A major concern with point estimation in general is that any time that we come up with a point estimate for a specific parameter, we know that that point estimate is not going to be exactly correct. This is just due to sampling variability. Every time you take a different sample, you're going to get a different point estimate. And so each time, we're not expecting to get exactly the right value, we're just expecting to get close to the right value. But this leads to a problem for us because a single number really doesn't tell us a whole lot about where do we expect this value to actually fall, how certain are we to have this number be close to the truth, how much uncertainty is there in this process in general. In place of doing point estimation, we can introduce the idea of interval estimation. And the idea with interval estimation is that we're still going to be estimating some parameter value. We still want to get at the value of an unknown parameter. However, instead of giving one value that we're guessing at, we're going to give a range of plausible values. So instead of saying we think that the population mean is 5, we're going to say we think that it's between 3 and 7. And by giving this range of values, we're doing a few things. First, we're quantifying our uncertainty, right? Wider ranges mean we're less certain, okay? And so we sort of get this quantification effect going on. But the other thing, and this is an important piece to note, is that it is possible for us to get the range correct, right? It is possible for the true value to fall within a range of values, even if we have sampling variability. The exact intervals that we're estimating might change from sample to sample. However, that doesn't mean that they can't contain the truth, or at least they can't often contain the truth. And so interval estimation takes this idea of guessing a parameter value using data, and instead of guessing a single value, we're going to turn and guess a range of values. So with point estimation, we attempted to guess one specific value, just a single number. We might get close to the truth, but we're not ever going to exactly guess it. And this is because of the sampling variability, right? The sampling variability means that we can never get exactly the right answer if we're using point estimation. Interval estimation is going to take this reality, the reality that we cannot actually get the exact answer correct, and work within it, right? We're going to say, okay, I can't get the exact answer correct, but I can give a range of values, and that range might be correct, right? Instead of having to nail down one specific value, we can give a range of values. Okay, so instead of attempting to guess whatever specific the value is, then we give this range. Across this whole range, we have a set of plausible values for the parameter. And the piece that becomes quite helpful for us is that we can quantify how certain we are that this range is actually going to contain the truth, right? If we take a really wide range, we should be more confident that in that very wide range, the true value actually lies than if we get a very narrow range. Right? And so we can come up with different intervals depending on how confident we need to be. If we need to be really sure that the true value falls somewhere in the interval we're giving, we can take a very wide interval. And by taking that very wide interval, we're sort of quantifying both the level of certainty that we have over this, but in so doing, we're also quantifying how uncertain or how much variability there is in these estimates, right? Because a wider interval means that we are going to have sort of more variability, right? There's more possible values or more plausible values for the truth. So there's a whole range of interval estimation techniques, but we are going to focus predominantly on the most common type of interval estimation, which is the confidence interval. So interval estimation is a range of possible procedures. Confidence intervals are just the most common application of interval estimation. So with a confidence interval, we want to think about this sort of in the most general terms possible to begin. And we're going to try to come up with how can we actually get a range of values using sort of the estimators. And if we think about theta hat being our estimator, theta hat is random, and so we can make probability statements about theta hat, right? So we could say that the probability that theta hat falls between A and B is equal to 1 minus alpha, right? And here, we don't know what these values of A and B actually are, right? We haven't sort of found them. But in theory, we could find what these are because theta hat is random, right? And so if we know what is the distribution of theta hat, right? What is their sampling distribution here? Then we could go to that sampling distribution and try to find values of B and A such that this statement actually holds, right? Such that we have some set probability of falling in this interval here. Now the values of a and b are going to be dependent on whatever we choose for our alpha here, right? So a and b aren't going to be constant, but they will be constant for any particular value of alpha that we can pick, right? And by setting up this statement here, what we're doing is we're forming an interval around some point estimator, right? Theta hat's a point estimator, and we can form some interval around it that holds with high probability. And all of this is based on the sampling distribution of theta hat, right? So the theta hat is the random component here. We can form an interval around theta hat. So when we form these values for a and b, almost always the values for a and b are going to depend on theta, right? They're going to be some function of theta. And this is because the sampling distribution for theta hat is almost always going to depend on theta. So if we think about something like the sample mean, for instance, right? The sample mean, if we use the central limit theorem, is going to be distributed according to an approximate normal distribution with a mean of mu and a variance of sigma squared divided by n. In our case here, right, theta hat is equal to x bar, and theta is equal to mu. Right? Now, because the sampling distribution depends on mu, then any of the values that we want to include for a and b are also going to have to depend on mu, right? And so because of this, a and b can be thought of as depending on the true value somehow. Okay, and so what we have here then is we have an interval of a less than or equal to theta hat, which is less than or equal to b, which we can sort of more accurately describe as some function of theta less than or equal to theta hat, which is less than or equal to b of theta, right? And so this interval, it's a little bit more clunky to write out in this way, but we should be thinking about that if you choose a different true parameter value, then you're going to end up with different values for a and b. Okay, so in terms of selecting alpha, right? Alpha can be any value between 0 and 1. If we take smaller values of alpha, then the probability that it falls into that interval is higher. If we take lower values of alpha, then it's going to be, or larger values of alpha, then it's going to be higher, right? So if you take alpha equals 0.5, then there's a 50% chance that you're in there. But if you take alpha equals 0.1, then there's a 90% chance we're in that interval, right? Because we're taking 1 minus alpha for that. And so any value between 0 and 1, in theory, could be worked with. And then what we're saying is that the interval a, b, right, so between the values of a and b, is going to contain the estimated value with a probability 1 minus alpha. The value that our estimator is going to take on, if we start calculating estimates from it, in 1 minus alpha proportion of the time, the value we estimate is going to be in this interval. Okay. And so if you think about going out and you take a bunch of different samples, and on each one of those samples you calculate theta hat, then between a and b, 1 minus alpha proportion of those samples should produce something within that interval. Okay. The rest of them, the other alpha proportion, are going to produce estimates that are outside of this interval. Right? And so that's what we're really saying here, is this is an interval not for the true parameter right now, but it's an interval for the estimates that we're generating. And this is an interval that is coming from the sampling distribution. We have to use our sampling distribution to derive this interval. Okay? Because it's an interval for the estimator and not an interval for the parameter itself, this isn't quite what we're looking for. We want an interval that is going to give us an interval around the true value, not around our estimated value, right? We want an interval that is something less than theta, less than b. Right? Instead, we have something less than theta hat, which is less than b. And so this isn't quite what we're looking for. But one thing that we can actually do in this situation is we can invert these intervals. And so let's take a look sort of more specifically at what we mean by this. So you can think about taking some quite straightforward interval here. Let's just say that we're going to take, say, 3 times theta is less than or equal to theta hat, which is less than or equal to 10 times theta, say. Okay, so we have this interval here. In this case, a is equal to 3 theta, and b is equal to 10 theta. right? And so what we can actually do here is we can think about, well, there's actually an interval around theta that's being implied. And so what do we mean by this? Well, let's just take this lower bound for a second, right? So what we know is that 3 theta is less than or equal to theta hat, right? And what if we wanted to express this as an interval for theta, right? What if we want to get theta all alone? Well, what this means is that theta is less than or equal to theta hat divided by 3. Okay, and so now what we have here is we have a statement that we can think about as being about the parameter. Theta hat, or theta has to be less than theta hat divided by 3. What about on the other side here, right? So on the other side, well, we had theta hat is less than or equal to 10 times theta. And so following the same procedure here, we get, well, theta hat, divide that by 10, divide both sides by 10 here. Theta hat divided by 10 is less than or equal to theta, right? And so what we have is that we've turned our two different bounds into bounds on the actual parameter. And so if I write this out, then this bound that was originally an upper bound is now giving a lower bound, and this bound that was originally a lower bound is now giving an upper bound. And so what we can say is that this is the same thing as saying theta divided by 10 is less than or equal to theta, which is less than or equal to theta hat divided by 3. Right? This interval is exactly the same mathematically as the interval that we started with up here. Right? If you know that theta hat falls between 3 times theta and 10 times theta, then you also know that theta falls between theta hat divided by 10 and theta hat divided by 3, right? These two things are mathematically equivalent. If one is true, the other one is true, right? And so we can say that if interval A holds, right, where what we're thinking about is this is interval A up here, then interval B holds. Right, where we're thinking about this as being interval B down here. And so because of this, these intervals are functionally the same thing. And so if we know, well, the probability that 3 theta is less than or equal to theta hat, which is less than or equal to 10 theta, if we know this probability is equal to, say, 0.9, right, then this is exactly the same thing as saying the probability that theta hat divided by 10 is less than or equal to theta, which is less than or equal to theta hat divided by 3, is also equal to 0.9, right? Because if one of the interval holds, both of the intervals hold. And so because of this, these intervals are interchangeable with one another. And if the probability for one is high, the probability for the other is exactly the same thing. Okay, and so this is the general theory that we're going to be using to form our confidence intervals here. The idea is that we're going to start with an interval around our estimator, right? So we start with an interval around theta hat here. We invert that so that it gives us an interval for theta. And then what we can say is that as long as this first interval holds with high probability, so too does this second one. Because this second one is now suddenly an interval that we can actually use for the parameter that we care about. Right? And so that's the basic idea that we're going to be following with confidence intervals. Now, fortunately, with confidence intervals, we've worked out what the confidence intervals are for a lot of parameters that we likely care about, but it's this underlying logic that's going to be quite important for us. And so just to reemphasize this logic, theta hat is random, so it has some sampling distribution, so we can make probability statements about it. So what we do is we make a probability statement that says theta hat's going to fall into some interval with high probability, and then we take that interval and we invert it so that it's really an interval about theta rather than theta hat. This, because they're mathematically the same, has to hold with the same probability. And so because of that, we're going to end up in a situation where we can say that this interval around theta is going to hold with high probability as well. And so that's the basic logic of confidence intervals, but we can sort of revisit these. Okay, so what we'll do here is we'll walk through the same idea sort of in more general terms now, right? So suppose that L of theta hat less than or equal to theta less than or equal to U of theta hat is an interval that arises from the inversion of A less than theta hat less than or equal to B of theta, right? And so this is the idea. We took 3 theta less than theta hat less than 10 theta, right? We inverted that to get theta hat over 10 less than or equal to theta less than or equal to theta hat over 3, right? And so we start with this interval here, and we invert it, and we get this interval here. Okay. Now, suppose that the original interval holds with some high probability, and we'll still take this probability to be 1 minus alpha. In the example we were just looking at, we took alpha to be 0.1, so that this was 90%, but it could be with any probability that we want here. Okay. Then what we know is that this other interval, this inverted interval, also has to hold with probability 1 minus alpha, right? It has to hold with the same 90% probability in the example we were considering. And so because of that, we now have an interval around theta that holds with high probability. This is a confidence interval for theta. It's an interval around our parameter that holds with high probability. Okay? So the endpoints, L of theta hat and U of theta hat, they're going to be random quantities. They depend on the point estimator that we have, right? Theta hat is random, and so if you take it and you transform it, it's still random. So we have 2 estimators going on here. We have a lower bound estimator that we're calling L of theta hat, and we have an upper bound estimator that we're calling U of theta hat. Both of these things are random. They both have their own sampling distributions. And so what we're actually saying here is that the L of theta hat being less than theta, this is one of the events that we're looking at, and then theta being less than U of theta hat is the other event, right? There's sort of still randomness in here, but the randomness comes from L of theta hat and U of theta hat, right? Theta here is still non-random. This is just some value that's not random. Okay, and so we can actually write this out into sort of this equivalent statement where we're saying, well, L of theta hat needs to be less than or equal to theta, right? And then U of theta hat needs to be greater than or equal to theta, right? And so then theta is U. And so this can be sort of this joint event that we're thinking about here, right? And it's just important to continually emphasize that in this quantity, the random components are L of theta hat and U of theta hat, right? L of theta hat and U of theta hat, because in this first interval, theta hat's the only thing that's random. Everything else is just a fixed constant. Okay? So taken together, we can refer to these as interval estimators, right? Because we have a lower bound and an upper bound. You put them together, that gives you an estimated interval. And if we select a reasonable alpha, then what we're saying is that we can be reasonably certain that these estimators are going to contain the truth between them, right? That the lower bound is going to be less than theta, the upper bound is going to be above theta, and so then between the two of them, we can be reasonably certain that the truth will fall. Okay. Now, confidence intervals are sort of a very deep topic. There's going to be a lot to explore there, but it's worth pausing and just taking some notes on the confidence intervals at this point. So the first thing is that 1 minus alpha, that's what we call the confidence level, right? So if you take 1 minus alpha to be 95%, then we'd say it's a 95% confidence interval. The confidence level is 95%, right? And the idea is that this should be selected based on context. In some contexts, you're going to want to be very certain that you contain the truth, right? If it's a very important situation, then maybe you want a 99% confidence interval or a 99.9% confidence interval, right? These are going to be very high levels of confidence because it's an important situation. If, on the other hand, it's a pretty low stakes scenario, then maybe you're happy with an 80% confidence interval or a 90% confidence interval, right? How confident you need to be depends not on the statistics of it. The statistics is happy to take any confidence level, but instead it depends on the context of what you're actually forming these confidence intervals for. So very commonly, we'll take 90, 95, or 99, but this should be selected on the basis of what's actually going on under the surface. Now, the interpretation of confidence intervals can get quite tricky, right? And the reason for this is because we've been talking about confidence intervals with a probabilistic interpretation, but once you actually have a confidence interval on hand, that probabilistic interpretation is going to fall down just a little bit. Because the only thing that is random is the actual estimators, right? Then once we're dealing with them as estimators, we can still use this probabilistic interpretation. However, this is the process that we're talking about, right? These are the estimators that we're talking about, and estimators are functions, they're processes. And so we can say that this process is going to produce an interval that has some high probability of containing the truth. However, as soon as we have a real interval in front of us, this is no longer the process anymore, right? Estimates are not random, and so then we can't use probabilities to talk about estimates. And so we have to be a little bit careful about the interpretation of confidence intervals, but that's a topic that's worth diving into in its own. So the overarching point here, though, is that a specific interval does not have a probability interpretation. However, the process of forming confidence intervals does. There's a lot more to be unpacked there, but at this point, just keep that in mind, right? The probability is coming from the estimators. The estimators are the processes. As soon as you're actually calculating specific estimates, you're not dealing with the estimators directly anymore. The construction of confidence intervals can also get quite tricky. So this process that we're walking through here, we haven't actually walked through for any specific parameter values, but it requires knowledge of the sampling distribution. It requires the inversion of those intervals that you find. It requires being able to find the interval in the first place and then sort of work from there, right? And so constructing these is not always going to be sort of a simple task. However, if we're dealing with common parameters, if we're dealing with sample means or proportions or variances or standard deviations, then fortunately, there are going to be well-defined confidence intervals for all of these parameters. And so these confidence intervals that are well-defined are going to be coming from this general process. The general process is going to work no matter what, but when you need a confidence interval for a mean, you don't actually have to go through this process. You can turn towards the process that's already been determined for the confidence interval for a mean. And so again, it's one of these things that as you continue to study confidence intervals, you're going to become more familiar with specific versions of this, and using those specific versions is going to be great, but it's important to fall back onto this general understanding of confidence intervals. There are also other approaches that are going to apply sort of more broadly for forming confidence intervals. These rely on some sort of more advanced statistical techniques. They can be quite useful if you ever need to form a confidence interval for a parameter that one does not really exist for. But again, they're going to be sort of approaches that try to take this process that we're talking about and formalize it in some way, right? So again, the underlying process is always going to be the same. You're going to find an interval for a statistic that's actually calculated on your data for some estimator, and then you're going to invert that so that it's an interval around a parameter. So the overarching summary so far is that confidence intervals are interval estimators, and they're interval estimators that have the size of the interval calibrated such that some set probability occurs with the true parameter falling within that interval, right? So that the interval that you're calculating contains the true parameter with some set probability. And then that way, when I give you a confidence interval, or I give you a procedure to calculate a confidence interval, you can be some level of certain that the true value is actually going to fall in there, right? And so it becomes this way of navigating around the difficulties of point estimation, where with point estimation, we know we're getting it wrong. With confidence intervals, we can say there's some probability that we're going to get this right. There's a 90% chance that we're getting it right, or a 95% chance we're getting it right, or a 99% chance that we're getting it right. And so confidence intervals are very useful for overcoming sort of the major downfall of point estimation. And because of that, they're quite handy in practice. However, they can be tricky. They can be tricky to actually calculate, and they can be tricky to interpret. And so studying them sort of in specific context makes overcoming those challenges a whole lot easier.